Have you ever stood on a beach and looked out towards the ocean and wondered, what is the farthest point that I can see? How far is that line called the horizon where the Earth's surface appears to meet the sky? Well, you can calculate that distance to the horizon. And you just need to use a little algebra and geometry. And that's what we're going to do today. All right, so let's draw Earth. We're going to assume it's a perfect sphere. And we're going to draw a person standing on the surface of the Earth. This picture is not to scale. And they look out from their eyes. And they look until they can see the horizon point, where the surface of the Earth appears to meet the sky. They can't see past that because the Earth curves and they can't see over the curve. Okay, so we're going to call that distance D, D for distance. That's what we're trying to find. For practical purposes, it's very similar in length to the arc length right along the surface of the Earth. So we'll just solve D, this straight line. Now, if you draw the radius of the circle to the horizon point, we'll call that R, and you draw the radius up to the surface where the person's standing as R for radius, and also add in the person's height above the surface, H, that's the height to their eyeballs, we actually have a right triangle that we can use for our calculation. Okay, and we can use the Pythagorean theorem, one of the big theorems in geometry that you may have heard of, which is a squared plus b squared equals c squared. Now, for our picture, if we swap in our values, that's r squared plus d squared equals r plus h squared. We'll expand that out a little bit. R squared plus d squared equals r squared plus 2rh plus h squared. Now we can simplify. These r squareds cancel out. This h squared here is a negligible value compared to everything else we're dealing with. A person's height in the context of the scale of the gigantic Earth and miles of the distance of the line of sight we're talking about is trivial. So we're just going to call that 0. And we're left with d squared equals 2rh. And d equals the square root of 2rh. Now we know what r is. We know what r is. R is 6,370 kilometers, or in meters, 6,370,000 meters. So we can plug that in, and we find that 2 times 6,370,000 times h. If we take the square root of that, we get d in meters equals 3,570 times the square root of the height in meters. And we can divide both sides by 1,000 to put the left side in terms of kilometers. So the distance in kilometers equals 3.57 times the square root of the height in meters. And that is our distance to the horizon formula. And it's remarkably close to the actual distance. We're not considering atmospheric effects or whether it's a clear day or not, but that is a pretty good rough estimate of how far you could see to the horizon. All right, so let's do an example if you're standing on the beach. Okay, say you're about 6 feet tall. You are standing on the sand. In meters, that's about 1.8 meters. So we go ahead and we plug that in up here in our equation, and we get 3.57 times the square root of 1.8, and that is about 4.8 kilometers, which is about 3 miles. And that's how far you can see to this horizon line. Now, if you're more comfortable working in feet and miles, that is perfectly fine. And you can just rewrite the equation we had before, but in miles and feet. And if you do all the conversions, it works out to 1.22 times the square root of the height of the observer's eyes in feet. So if we want to do an example with Mount Kilimanjaro, we see that the height of Mount Kilimanjaro at the peak is 19,341 feet. If we plug that in, we see that on a clear day without any obstructions, you can see to the horizon for about 170 miles. So if you like learning about Earth, go check out veryberrylabs.com and click on the book I published last year called Thinking Through Planet Earth, which answers the question, if you dig to the other side of the planet, where do you end up? Check that out, and I will see you on the other side.